here we go.
There is something very important I want to discuss. You might have seen in the assignment that we had a training set, as well as a validation set, and a test set. What is that all about? Don't skip that part. It has to do with measuring how well you're doing without accidentally shooting yourself in the foot. And it is a lot more subtle than you might initially think. It's also very important because, as we will discover later, once you know how to measure your performance on a problem, you've already solved half of it. Let me explain why measuring performance is subtle. Let's go back to our classification task. You've got a whole lot of images with labels. You could say, okay, I'm going to run my classifier on those images and see how many I got right. That's my error measure. And then you go out and use your classifier on new images that you've never seen in the past. And you measure how many you get right, and your performance gets worse. The classifier doesn't do as well. So what happened? Well, imagine I construct a classifier that simply compares the new image to any of the other images that I've already seen in my training set, and just returns the label. By the measure we defined earlier, it's a great classifier. It would get 100% accuracy on the training set. But as soon as it sees a new image, it's lost. It has no idea what to do. It's not a great classifier. The problem is that your classifier has memorized the training set, and it fails to generalize to new examples. It's not just a theoretical problem. Every classifier that you will build will tend to try and memorize the training set, and it will usually do that very, very well. Your job, though, is to help it generalize to new data instead. So, how do we measure the generalization instead of measuring how well the classifier memorized the data? The simplest way is to take a small subset of the training set, not use it in training, and measure the error on that test data. Problem solved. Now your classifier cannot cheat because it never sees the test data, so it can't memorize it. But there is still a problem, because training a classifier is usually a process of trial and error. You try a classifier, you measure its performance, and then you try another one, and you measure again, and another, and another. You tweak the model, you explore the parameters, you measure, and finally, you have what you think is the perfect classifier. And then after all this care you've taken to separate your test data from your training data and only measuring your performance on the test data, now you deploy your system in a real production environment, and you get more data, and you score your performance on that new data, and it doesn't do nearly as well. What can possibly have happened? What happened is that your classifier has seen your test data, indirectly through your own eyes. Every time you made a decision about which classifier to use, which parameter to tune, you actually gave information to your classifier about the test set. Just a tiny bit, but it adds up. So over time, as you run many and many experiments, now your test data bleeds into your training data. So what can you do? There are many ways to deal with this. I'll give you the simplest one. Take another chunk of your training set and hide it under a rock. Never look at it until you've made your final decision. You can use your validation set to measure your actual error, and maybe the validation set will bleed into the training set. But that's okay, because you always have this test set that you can rely on to actually measure your real performance.
Mm-hmm. Gotcha.
I'm not going to talk about cross-validation here, but if you've never encountered it in your curriculum, I'd strongly recommend that you learn about it. I am spending time on this because it's essential to deep learning in particular. Deep learning has many knobs that you can tweak, and you will be tempted to tweak them over and over. You have to be very careful about overfitting on your test set. Use a validation set. How big does your validation and test sets need to be? It depends. The bigger your validation set, the more precise your numbers will be.
Okay.
Does splitting your data into 3 separate data sets sound overly complicated? Let's look at this in action in the real world. Kaggle is a competition platform for machine learning. People compete on classification tasks, and whoever gets the highest performance wins. Here I'm showing the example of a scientific competition on data that relates to the Higgs boson. Kaggle also has 3 data sets: the training data, the public validation data set, and a private test set that is not revealed to the competitors. Here, Kaggle shows you the performance of the top competitors when measured on the private test sets. The green and red arrows show how different their ranking was compared to the ranking on the public set. Let's look at the rankings. The top competitors were doing well on the public validation data, and they remained at the top once the private data was revealed. If you go further down the leaderboard, however, it's a real bloodshed. Many competitors who thought they were doing well were not doing well at all on the private dataset. As a result, their ranks went down dramatically once the private dataset was revealed. Why is that? Maybe they had a good model that did well in validation just by chance. What's more likely, however, is that by evaluating themselves over and over dozens of times on the validation set, they ended up overfitting to the validation set and failing to generalize. The few top competitors, however, had good experimental design. They were not misled into thinking that they were doing well. They probably took out some of the training set to validate their algorithm, or used more sophisticated methods like cross-validation, and didn't make many decisions based on the public dataset scores. Imagine that your validation set has just 6 examples with an accuracy of 66%. Now you tweak your model, and your performance goes from 66% to 83%. Is this something you can trust? No, of course. This is only a change of label for a single example. It could just be noise. The bigger your test set, the less noisy the accuracy measurement will be. Here's a useful rule of thumb. And if you're a statistician, feel free to cover your ears right now. A change that affects 30 examples in your validation set, one way or another, is usually statistically significant and typically can be trusted. Let's do some back-of-the-envelope calculations. Imagine you have 3,000 examples in your validation set, and assume you trust my hand-wavy rule of 30. Which level of accuracy improvement can you trust to not be in the noise? A difference from 80% to 81%, a difference from 80% to 80.5%, a difference of 80% to
Wait, I missed that previous one. Let's go back.
Imagine that your validation set has just 6 examples with an accuracy of 66%. Now you tweak your model, and your performance goes from 66% to 83%. Is this something you can trust? No, of course. This is only a change of label for a single example. It could just be noise. The bigger your test set, the less noisy the accuracy measurement will be. Here's a useful rule of thumb. And if you're a statistician, feel free to cover your ears right now. A change that affects 30 examples in your validation set, one way or another, is usually statistically significant and typically can be trusted.
What? 30?
Let's do some back-of-the-envelope calculations. Imagine you have 3,000 examples in your validation set, and assume you trust my hand-wavy rule of 30. Which level of accuracy improvement can you trust to not be in the noise? A difference from 80% to 81%, a difference from 80% to 80.5%, a difference of 80% to 80.1%.
30 is 1%. So this you would trust, this you would not, and this you would not, because this has changed 1%, which is more than the rule of 30, and these you would not trust because it's less than 1% change. Where does he get like the number 30 from?
If your accuracy changes from 80% to 80.1%, that's only at most 3 examples changing their labels. It's 0.1 times 3,000 divided by 100. That's very few. It could just be noise. And it definitely doesn't meet my rule of thumb of 30 examples minimum. Same thing going from 80% to 80.5%. At worst, only 15 examples are changing then. When you get an improvement of 1%, going from 80% to 81%, that's now a more robust 30 examples that are going from incorrect to correct. That's a stronger signal that whatever you're doing is indeed improving your accuracy.
Cool.
This is why for most classification tasks, people tend to hold back more than 30,000 examples for validation. This makes accuracy figures significant to the first decimal place and gives you enough resolution to see small improvements. If your classes are not well balanced, for example, if some important classes are very rare, this heuristic is no longer good. Bad news, you're only going to need much more data. Now, holding back even 30,000 examples can be a lot of data if you have a small training set. Cross-validation, which I've mentioned before, is one possible way to mitigate the issue. But cross-validation can be a slow process, so getting more data is often the right solution.
Validation set.
With that out of the way, let's go back to training models. Training logistic regression using gradient descent is great. For one thing, you're directly optimizing the error measure that you care about. That's always a great idea. And that's why in practice, a lot of machine learning research is about designing the right loss function to optimize. But as you might have experienced if you've run the model in the assignments, it's got problems. The biggest one is that it's very difficult to scale. The problem with scaling gradient descent is simple. You need to compute this gradient. Here's another rule of thumb. If computing your loss takes n floating point operations, computing its gradient takes about 3 times that compute. As we saw earlier, this loss function is huge. It depends on every single element in your training set. That can be a lot of compute if your data set is big. And we want to be able to train on lots of data because in practice, on real problems, you'll always get more gains the more data you use. And because gradient descent is iterative, you have to do that for many steps. That means going through your data tens or hundreds of times. That's not good. So instead, we're going to cheat. Instead of computing the loss, we're going to compute an estimate of it. A very bad estimate. A terrible estimate, in fact. That estimate is going to be so bad, you might wonder why it works at all. And you would be right, because we're going to also have to spend some time making it less terrible. The estimate we're going to use is simply computing the average loss for a very small random fraction of the training data. Think between 1 and 1,000 training samples each time. I say random because it's very important. If the way you pick your samples isn't random enough, it no longer works at all. So we're going to take a very small sliver of the training data, compute the loss for that sample, compute the derivative for that sample and pretend that that derivative is the right direction to use to do gradient descent. It is not at all the right direction. And in fact, at times, it might increase the real loss, not reduce it. But we're going to compensate by doing this many, many times, taking very, very small steps each time. So each step is a lot cheaper to compute, but we pay a price. We have to take many more smaller steps instead of one large step. On balance, though, we win by a lot. In fact, as you'll see in the assignments, doing this is vastly more efficient than doing gradient descent. This technique is called stochastic gradient descent and is at the core of deep learning. That's because stochastic gradient descent scales well with both data and model size, and we want both big data and big models. Stochastic gradient descent, SGD for short, is nice and scalable, but because it's fundamentally a pretty bad optimizer that happens to be the only one that's fast enough, it comes with a lot of issues in practice.
Okay.
You've already seen some of these tricks. I asked you to make your inputs zero mean and equal variance earlier. It's very important for SGD. I also told you to initialize with random weights that have relatively small variance. Same thing. I'm going to talk about a few more of those important tricks, and that should cover all you really need to worry about to implement SGD. The first one is momentum. Remember that at each step, we're taking a very small step in a random direction, but that on aggregate, those steps take us towards the minimum of the loss. We can take advantage of the knowledge that we've accumulated from previous steps about where we should be headed. A cheap way to do that is to keep a running average of the gradients and to use that running average instead of the direction of the current batch of the data. This momentum technique works very well and often leads to better convergence. The second one is learning rate decay. Remember, when replacing gradient descent with SGD, I said that we were going to take smaller, noisier steps towards our objective. How small should that step be? That's a whole area of research as well. One thing that's always the case, however, is that it's beneficial to make that step smaller and smaller as you train. Some like to apply an exponential decay to the learning rate. Some like to make it smaller every time the loss reaches a plateau. There are lots of ways to go about it, but lowering it over time is the key thing to remember.
Let me check something for a sec. Settings. Okay.
You've already seen some of these tricks. I asked you to make your inputs.
Already seen that, man.
Learning rate tuning can be very strange. For example, you might think that using a higher learning rate means that you learn more or that you learn faster. That's just not true. In fact, you can often take a model, lower the learning rate, and get to a better model faster. It gets even worse. You might be tempted to look at the curve that shows the loss over time to see how quickly you learn. Here, the higher learning rate starts faster, but then it plateaus, when the lower learning rate keeps on going and gets better. It is a very familiar picture for anyone who's trained neural networks. Never trust how quickly you learn. It has often little to do with how well you train. This is where SGD gets its reputation for being black magic. You have many, many hyperparameters that you could play with. Initialization parameters, learning rate parameters, decay, momentum, and you have to get them right. In practice, it's not that bad. But if you have to remember just one thing, is that when things don't work, always try to lower your learning rate first. There are lots of good solutions for small models, but sadly none that's completely satisfactory so far for the very large models that we really care about. I'll mention one approach called Asteroid that makes things a little bit easier. Asteroid is a modification of SGD, which implicitly does momentum and learning rate decay for you. Using Asteroid often makes learning less sensitive to hyperparameters, but it often tends to be a little worse than precisely tuned SGD with momentum. It's still a very good option, though, if you're just trying to get things to work. So let's recap. We have this very simple linear model which emits probabilities, which we can use to classify things. We now know how to optimize its parameters on lots and lots of
input, linear model, right. Softmax was then the, yeah, got that one. Cross entropy. Yeah, this just says like this is the hot label. Okay.
Some data using SGD and its variance. It's still a linear, shallow model though, but now we have all the tools that we need. It's time to go deeper.
Awesome. Play next. It was good, man. Send and continue.
Welcome to the walkthrough for assignment number 1 of the deep learning.
I think I've done all of this.
I hope you're enjoying the lectures so far. The first assignment, which you can go and take a look at on the TensorFlow, what your machine looks like, Docker use is called not a nest.
Yeah.
Letters that are rendered in. This is simply.
I've done this. How to display an image within a notebook. insert a code cell by clicking on that. You'll need a display method and image type from. Oh, you just go through all the.
Extracting those images from the data sets. It will create in your local directory 2 directories, not mnist large, which is the training data, mnist small, which is then the training data. Each of those directories have 10 subdirectories, one for each. It's good to be able to visualize it in your notebook. You can use ipython.display to display an image and convince yourself that you've got things.
Yeah.
The next step is going to be to convert that data into a format that's a lot easier to manipulate. Okay? So we're going to convert every image dataset into a multi-dimensional array where you want your data to basically for each of the letters of each dataset.
Yeah, done that.
You do want to make sure that your data at the end of the day still looks good, so it's a good idea to visualize that those little tensors that you've created still contain the right information. So let's try.
Yes.
You also want to make sure that you've got data from all the different classes that you care about. We expect those classes to be roughly balanced in terms of the number of...
yeah, got that as well.
The next step is going to actually create the datasets that we are going to be using to train, validate, and test our class to make it smaller.
I've done all of these.
Let's see. Problem 5 now is about looking a little bit more deeply at the data. So
I haven't done this one yet, though.
Problem 6 is the first really foray into trying to do machine learning on the problem. If you're going to embark into solving a problem using machine learning, it's a really good idea to start simple and actually convince yourself that machine learning can solve your problem, and that the data is actually fit for being treated as a machine learning problem. That you should
start with that first.
That you don't have one feature in your data that is going to allow you to solve the problem in a trivial way, and that you will get 100% accuracy, but that feature actually is something that you might not be able to have at test time. So let's try a very simple model, and one, for example, that you can consider is the logistic regression that's in sklearn. Sklearn is a package that's very popular, that has a lot of already pre-implemented machine learning approaches. You can call the function fit, and it will fit a model to its input-output pairs. That's basically training. You can also call score, and that's just saying give it a test data and test labels, and it will return the accuracy of your model on that data. So it's very simple, 4 lines of code, 5 lines of code, and you can basically run a small classifier on your data and convince yourself that there's actually something to learn here. Next assignment will be to actually start using this data and implementing your own logistic regression and subsequently deep learning models.
All right. Okay, so what did he suggest here?
Try a very simple model, and one, for example, that you can consider is the logistic regression that's in sklearn.
Okay, let's give that a shot. Let's give that a shot, guys. That was here. But the problem was that I need to load in all the data again. Or did I pickle them eventually? No. No. Nope. Nope, 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 nope. Maybe here. Pickle file. And this should work. Pickle is not defined. That's correct. So while or with open pickle, not mnist.pickle, read, load again, pickle.load f. Yes. Ran out of input. I think, yeah, no, the file was empty. That was the problem. The file was empty. So I would need to rerun. Let me just have a look here, because here we extracted all the files. Let's go back to the start. So the first part was downloading them. Then we extracted the files. And then we said load them and pickle the folders, or maybe pickle. Yeah, right, okay. So I should be able to read them from the file, I think. But I just rerun this part. It could take out, no, train folder is not defined. I don't think I'm gonna rerun all of it again because it took ages. Yeah, so the file name, train file name, that's what maybe download returns. Destination file name. Because this downloads it. And that is the file name. So maybe if I say, simply something like that. And then I can extract it. Already present. What's this? Okay. Seems good to me. We'll hit this again. Pickle already present, skipping pickling. Let's verify the data looks good. Let's verify that. Okay. Run that again. Okay. And then this part was, I think, actually pickling the files. So awesome. Cool. And randomize, I think it just shuffles them. And then this was this. This is a 4. Oh no. Yeah, no, it's just 3. It's just 3. It's a 3, but it how does it work again? It starts at 0, I guess. So it's 0, 1, 2, 3, 4. So it's the 4th. It's always one more, I guess. Let's have a look. I don't even know what that is myself, so. E. Oh no, so there's not. Oh god, they're not actually numbers there. They're letters, okay. So that's the 4th letter, A, B, C. A 0 is an A, so it's A, B, D, C. Okay, that makes sense. Let's go back to that one to make sure that one. So that's also an E, I guess. Sure. And that's an F, it comes after E. Okay. Let's save the data for later reuse. Oh, yeah, I still need to do that. There you go. For later reuse. Done. I don't need that anymore. Give me a sec, guys. Give me a sec, guys. Okay. Awesome. Okay. So these were the duplicates. Problem 6. Let's get an idea of what an off-the-shelf classifier can give you on this data. It's always good to check that there's something to learn. All right. So I have train dataset, which is a NumPy array of shape 200,000 2828. Yes, I understand that one. And then you also have the train labels, which just has, okay, that just contains the label of the number that it, or the letter that it should be. So 4 means E, and so on. 9 means whatever. All right, using 50, 100,000, 5,000 training samples, and you can use logistical regression from the linear model. Okay, so we're going to import from SK. Let's have a look. Linear model. This one. So from learn linear model. And let's see how we have to use this. This is just a plain ordinary least squares wrapped as a predictor object. Okay, so we can fit. I think all I need to do is just fit and pass in the train set and the target set. And then I can say, give me the score for the tests. I think it actually is just that easy. At least that's what they were saying, so I would hope so. Okay, so L equals linear regression, and I can say L dot fit, training set being train data sets, no, data set, and then you have train labels. Right. Nope. Missing one required positional argument, Y. Okay. Fit X and Y. Oh, I think I maybe need to say Y equals. Nope. Train labels. NumPy array of sparse matrix. So this makes sense, but this, I think I need to reshape it. So that would be train dataset shaped equals train dataset dot, is it reshape? Yes. And then it's 200,000. How do you do this? Was it just like that? Is that just it or no? Train data set dot reshape returns an array containing the same data with a new shape. Refer to numpy.reshape for full documentation. So the shape, is it like that? I think is, or just get rid of this. Or is it, it's something like that. It's something where you say, oh, like that. Well, let's go up here and say numpy. Or is np? Gives a new shape to an array without changing its data. I really liked, okay, new shape, int, or tuples of ints. Oh, yeah. I thought I need to say 200,000 and then 28 times 28. Okay. Thank you. But it still won't work, I think, because I'm missing a required argument. Why? But why? Linear regression. Oh, how did I do that? Self. What? No. What? Signature, self, x, y, sample weight. Wow, this is amazing. Shift tab. Press shift tab twice. Beautiful. Fucking beautiful. All right. NumPy array or sparse. Oh, yeah. Okay, so I got this. There's, oh, but of course I need to give it a different one. And then this one needs to be n samples of n targets. Train labels. What am I doing? Dot shape. I think that's the correct. Self. What's self? I'm not sure. Is there examples of the like full code examples here somewhere? There is. Let's have a look at this one. So linear model. Yeah. Yeah. Some music. Well, I didn't do a fit here, so that's not very useful. A fit transform. Whatever. Fit. Linear regression example. Yes, please. Fit. Let's look this up. I don't think we should spend too much time on this. Well, how do they... Oh, hang on. I need to add... L.score. Was that it? Score. Oh. Hey. Need to pass it the test dataset and the test labels. Shall also need to reshape, I think. So I don't know what the length is of test data set, but there you go. Bum. Bum. We actually need to add that back in there. Okay. Nope. Oh. Find array with 3 dimensions, estimated expected. Is shaped. No, underscore shaped. 46%. It's brilliant. Perfect. Actually add that. Actually add it to the same line, I think. Just add it there. I can say, get rid of that, run that, and it just spits out a number. Eventually. I think it went a little faster this first time. Oh, but I am training on all the data though. Oh, but I need to use logistic regression. Ooh. Or at least that's what they're telling me to do. Logister. This won't work, will it? Or will it? Can't I get more confusion matrix? Still churning through that code. Now this is R, I think. Okay. Escape learn. That's still going. Compute the confusion matrix to evaluate accuracy of a classification. By definition, the confusion matrix is such that is equal to the number of observations and to be the group, whatever. Right. Parameters. Yeah. I think I know what this means. So I'll say import that. Well, that's what it outputs, does it? No, that's actually not what I meant. I just meant the precision recall. Still going. Maybe I shouldn't have done that for all the data. Oh. Okay, I think it's this one. So that's the true, predicted, how did I do that? I should go to my post and check it out. This one. So you fit it, you predict the values expected, and then you say classification report. Okay. It's this one. And then I would say predictions split, and then this. Cool. Digits would be the test data set shaped. I think. And CLF would be L.
Met Spotify Premium is er altijd muziek. Luister overal, ook zonder internetverbinding. Probeer Premium gratis.
All the answers are in labels. Right. That's what the expected labels are. So I don't need to change that. Let's just test labels. This is taking quite long though. Maybe I should reduce the number of...
Belevenis van de week bij Albertijn. Hollandse bingo. Want bij elke €10 aan boodschappen ontvang je 2 bingo-zegels.
Ja.
Kaart vol? Bingo! Dan ontvang je 24 producten helemaal gratis. Ontdek alle voorwaarden in de winkel of op ah.be. Gewoon bij Albertijn.
There are 200,000 records though, so maybe it doesn't scale as such. Let's interrupt it. Interrupt. And then I'll say doesn't even want to interrupt. Good. train dataset. No, I'll just do it here. So I'll say 100 or 1,000. Oh God. I can't stop it. No. Restart the kernel. Guys. $2.5 gigs. I think I'll have to, man. Oh, wait, it can't stop. I can't even stop it. Can it? Oh, there he goes. Wow. Okay. So I'll have to go through these steps one more time. Which is no problem because it takes seconds anyway. Do that one. Can do this one. Do that one. Do that one. That one. Randomize it. Randomize it. Okay. Watch that one. Watch that one as well. Okay. We'll reshape it. Yes, I think this should go a lot faster because there's only 1,000 records. Let's try 5,000. So it's 5,000. Let's see if the score goes up or down. It was 83. That's a lot slower. Went up. Okay, let's see what this does. Oh, we're on Python 3, aren't we? Excuse me. Okay, so we have 1,000 records for each label. And looking at this, let's look at the F-score first. This one does pretty well. And, well, I guess this one as well. The one that does least well is 8. 8. A, B, C, D, E, F, G, H. I. It's 8, but it's actually 9. Okay, so it's the I. It struggles with the I. And the precision is actually quite low. But let's actually bump it up a bit. We'll say 10,000. Don't need to do that. The test dataset is not really a problem, is it? We're at 85% now. Still training. Oh. Did it work? I think it did. We'll predict them. Pretty much same story. It does look like the eye catched up. This one is a quite interesting one. Big difference between precision and recall. The 4 is the E. Yeah. It's the one that does least well, it looks like, together with the I. Awesome. Maybe we should try a random forest as well, see what that does. So let's see, how do we do that? Okay. So from that, import that. And how does that one work? Fortunately, I've done this one before, so I could pretty much just copy paste the code, but maybe it's just the same way. Maybe it's just the same code, so we'll just copy paste it. We'll say random forest equals random forest classifier. And I think you need to pass a number of estimators here. Okay, it's defaulted to 10. Sure. Well, yeah, no, that's fine. And then we'll train it. Let's see how long that takes. Oh, hang on. I'm not gonna put it there. I'll put it here and I'll say, oh, I'm training the other one again. RF, actually then I can't put it in there. RF, I have to wait. $10,000 examples. And it's only doing 10 iterations, so it shouldn't take that long. But it would be interesting to see how much better it does than the, or if it even does better than the linear model, the logistic model. Okay, let's run it again. Wow, actually much faster. Then we can probably bump this up to about 20,000, maybe even more. 90. I say we bump it up even more to, alright, maybe bump up the estimators. What's it called? Master matrix. Now it's 10, let's put it to 100. This will take much longer though. Should be about 10 times as long. $93. Wow. 95% precision on the 7. %96% on the C. Wow. Still kinda struggles with the I, which is strange, and you would think that the I is pretty. It is an I though, isn't it? One, two, three, four, five, six. B, C, D, E, F, G, H, I, J. Yeah, so it's 4. It's the I, wow. So it kind of struggles with the I, where you wouldn't think that. You would think that it. The C, it does very well. The A does very well. Yeah. I'm gonna bump it up again to 40,000. Run it again. Bam! This will take a while. Okay. So that's cool. Nope.
Problem 6 is the first really foray into trying to do machine learning on the problem. If you're going to embark into solving a problem using machine learning, it's a really good idea to start simple and actually convince yourself that machine learning can solve your problem, or that the data is actually fit for being treated as a machine learning problem, that you haven't messed up, or that you don't have one feature in your data that is going to allow you to solve the problem in a trivial way, and that you will get 100% accuracy, but that feature actually is something that you might not be able to have at test time. So let's try a very simple model, and one, for example, that you can consider is the logistic regression that's in sklearn. In the last lesson, we've trained a simple logistic classifier on images. Now we're going to take this classifier and turn it into a deep network. And it's going to be just a few lines of code, so make sure you understand well what was going on in the previous model. In the second part, you're going to take a small peek into how our optimizer does all the hard work.
So the linear model was, I think, 80% score. The logistical model was 86. The random forest got up to 94. Probably a lot more if I train it on all of the data, which I'll actually do right now. And then we'll see what the neural network will be able to do. This is going to take a while, but let's just run it. Cool.
For you, computing gradients for arbitrary functions. And then we're going to look together at the important topic of regularization, which will enable us to train much larger models.
Okay.
The simple model that you've trained so far is nice, but it's also relatively limited. Here's a question for you. How many trained parameters did it actually have? As a reminder, each input
3
was a 28 by 28 image, and the output was 10 classes. Enter the number of parameters here.
Number of parameters. Yes, there was 10 classes. So Number of parameters? So 28 times 28. Well, so I think you have 784, but then plus the weight and the bias. I'm gonna say, no, that doesn't make sense. I'm gonna say 786. Think about which components in this equation define the model. How many elements do they have in total? Think about which components in this equation define the model. Three? I see it. So 784, is that it? No? Times 3? Is that it? 2325. View answer.
The matrix W here takes as an input the entire image, so 28 by 28 pixels. The output is of size 10, so the other dimension of the matrix is 10. The biases are just 1 by 10. So the total number of parameters are 28 by 28 by 10, plus another 10. That gives you 7,850.
There you go. This guy's still training.
That's the case in general. If you have n inputs and k outputs, you have n plus 1 times k parameters to use, not one more. The thing is, you might want to use many, many more parameters in practice. Also, it's linear. This means that the kind of interactions that you're capable of representing with that model is somewhat limited. For example, if two inputs interact in an additive way, your model can represent them well as a matrix multiply. But if two inputs interact in a way that the outcome depends on the product of the two, for example, you won't be able to model that efficiently with a linear model. Linear operations are really nice, though. Big matrix multiplies are exactly what GPUs were designed for. They're relatively cheap and very, very fast. Numerically, linear operations are very stable. You can show mathematically that small changes in the input can never yield big changes in the output. The derivatives are very nice too. The derivative of a linear function is constant. You can't get more stable numerically than a constant.
I don't know what you're talking about, man.
So we would like to keep our parameters inside big linear functions, but we would also want the entire model to be nonlinear. We can't just keep multiplying our inputs by linear functions, because that's just equivalent to one big linear function. So we're going to have to introduce nonlinearities. Let me introduce you to the lazy engineer's favorite nonlinear function, the rectified linear unit, or ReLU for short. ReLUs are literally the simplest nonlinear functions you can think of. They're linear if x is greater than 0, and they're the 0 everywhere else. ReLUs have nice derivatives as well. Which of these plots do you think best represents the derivative of a ReLU?
I don't even know what a derivative is, man. Math derivative. Simple English. simple Wikipedia.org. Is that a language that... Is this that language that people created? No. No, never mind. Is a way to represent rate of change. That is, the amount by which a function is changing at one given point. For functions that act on real numbers, it is the slope of the tangent line at a point on a graph. The derivative is often written using dy over dx, meaning the difference in y divided by the difference in x. The d's are not variable and therefore cannot be cancelled out. Are constant. That is, the derivative in one spot on the graph will remain the same on another. Yeah, because that's the rate of change. So a function the graph of a function can go up, but the rate of it going up will always be the same because it's a straight line. So, oh, there you go. 96%. That's the score to beat then. 96. I'll try with less estimators. Okay. So, the derivative of this thing. Oh, yeah. So that's this one, isn't it? Because it's the derivative. Oh, it's definitely that one.
When x is less than 0, the value is 0. So the derivative is 0 as well. When x is greater than 0, the value is equal to x. So the derivative is equal to 1. The second answer is the right answer.
I figured that one out by myself. Wow.
Because we're lazy engineers, we're going to take something that works, our logistic classifier, and do the minimal amount of change to make it nonlinear. We're going to construct our new function in the simplest way that we can think of. Instead of having a single matrix multiply as your classifier, we're going to insert a ReLU right in the middle. We now have two matrices, one going from the inputs to the ReLUs, and another one connecting the ReLUs to the classifier. We've solved two of our problems. Our function is now nonlinear, thanks to the ReLU in the middle, and we now have a new knob that we can tune, this number h, which corresponds to the number of ReLU units that we have in the classifier. We can make it as big as we want. Congratulations, you've built your first neural network. You might ask, wait a minute, where's my neuron? In the past, when talking about neural networks, I remember seeing diagrams with dendrites, axons, activation functions, brains, neuroscience. Where is all that?
That's not completely clear to me, but it might become clear. So let's just keep going.
Yes, I could talk about neural networks as metaphors for the brain. It's nice, and it might even be true. But it comes with a lot of baggage, and it can sometimes lead you astray. So I'm not going to talk about it at all in this course. No need to be a wizard neuroscientist. Neural networks naturally make sense if you're simply a lazy engineer with a big GPU who just wants machine learning to work better. Now, though, is a good time to talk about the math.
Oh no! A two-layer neural network. Depicted above is a two-layer neural network. The first layer effectively consists of the set of weights and biases applied to X and passed through ReLUs. Okay, the output of this layer is fed to the next one, but it is not observable outside the network, hence it is known as a hidden layer. The second layer consists of weights and biases applied to these intermediate outputs, followed by the softmax function to generate probabilities. Yeah.
One reason to build this network by stacking simple operations, like multiplications and sums and ReLUs on top of each other, is that it makes the math very simple. Simple enough that a deep learning framework can manage it for you. The key mathematical insight is the chain rule. If you have two functions that get composed, that is, one is applied to the output of the other, then the chain rule tells you that you can compute the derivatives of that function simply by taking the product of the derivatives of the components. That's very powerful. As long as you know how to write the derivatives of your individual functions, there is a simple graphical way to combine them together and compute the derivative for the whole function. There's even better news for the computer scientist in you. There is a way to write this chain rule that is very efficient computationally, with lots of data reuse, and that looks like a very simple data pipeline. Here's an example. Imagine your network is a stack of simple operations, like linear transforms, ReLUs, whatever you want. Some have parameters, like the matrix transforms, some don't, like the ReLUs. When you apply your data to some input X, you have data flowing through the stack up to your predictions Y. To compute the derivatives, you create another graph that looks like this. The data in that new graph flows backwards through the network, gets combined using the chain rule that we saw before, and produces gradients. That graph can be derived completely automatically from the individual operations in your network. So most deep learning frameworks will just do it for you. This is called backpropagation, and it's a very powerful concept. It makes computing derivatives of complex function very efficient, as long as the function is made out of simple blocks with simple derivatives. Running the model up to the predictions is often called the forward prop, and the model that goes backwards is called the backprop. So to recap, to run stochastic gradient descent, for every single little batch of your data in your training set, you're going to run the forward prop and then the back prop, and that will give you gradients for each of your weights in your model. Then you're going to apply those gradients with a learning rate to your original weights and update them. And you're going to repeat that all over again many, many times. This is how your entire model gets optimized. I am not going to go through more of the math of what's going on in each of those blocks, because again, you don't typically have to worry about that, and it's essentially the chain rule. But keep in mind this diagram. In particular, each block of the back prop often takes about twice the memory that's needed for the forward prop, and twice the compute. That's important when you want to size your model and fit it in memory, for example.
Train a fully connected network using gradient descent and stochastic gradient descent. The assignments in this course build on each other, so please finish assignment 1. Excuse me. Starter code. Open the Python notebook for this assignment, fully connected, and follow the instructions to implement and or run each indicated step. Some steps have been implemented for you. Okay. This is a self-evaluated assignment. As you go through the notebook, make sure you are able to solve each problem and answer any posed questions. Save your response as marked down in the notebook. Your new model should perform better than the one you developed for assignment 1. Also, the time required to train using stochastic should be considerably less than the simple gradient descent. I don't know, 96%. I guess we'll just have to see about that. I'll save it. And I can close and hold this one. Okay. Using TensorFlow. I'm gonna go through all of this tomorrow, but now my brain is fried. There you go. So we've still got this assignment to go. Then there's another assignment down here, regularization. Then they move into convolutional neural networks. Cool. And there's a section on deep models for text and sequences. That's pretty interesting. I think some of these words I recognize, so done some of these at work. At LSTM, the word to vec, stuff like that. Software and tools. And there's a project down here, build a live camera app. Cool. Well, thank you guys for watching. See you next time.